Lesson 14 is where we're really getting into the bit of a kind of more straightforward stuff that's a little more intuitive. And then with that normal curve that you're probably used to seeing, the bell-shaped curve. And then we're going to be sticking with that for pretty much the rest of the semester. So 12 and 13 are the new material that you may not have ever seen. It's definitely not as intuitive. So this is kind of that one-off. So just stick with it. I promise you, lesson 14, it's going to be a lot more smooth sailing. Well, okay, I shouldn't promise that. I hope that it will be a lot more smooth sailing. Okay, so let's talk about lesson 12. So lesson 12, we're talking about discrete probability distributions. Okay, so earlier when we learned about quantitative variables, we classified them as interval or ratio, right, where the ratio variables had the true zero. Okay, now we're talking about variables that are either discrete or continuous. And it's not just quantitative. Sometimes we're dealing with qualitative variables as well. Right now it's a different way to classify things, as either discrete or continuous. So I've got some examples here where I've got the same type of thing, people in the room, a speech for your class, eggs laid by a hen. So I've got three of the same variables that we're looking at two different ways. If we're looking at it and number of people in the room, I can look at it as a discrete variable by just looking at how many people are in the room. But if I want to take those same people and make it continuous, I can look at the height of each person. For a speech, I can look at the number of times a person says in a speech versus how long that speech took. So I'm looking with the eggs of a hen, I can look at how many eggs the hen lays, or I can look at the weight of each egg laid by the hen. Hopefully you notice that pattern. The discrete variables tend to say the number of times, the number of something, whereas continuous is a growth, is really growth in time, growth in weight, height, those kinds of things that you can measure, or use a stopwatch or a measuring tape. Really, if you start with a sentence with the number of, anything you put after that, the number of blank, really the number of anything, the number of cars in a parking lot. But there's other discrete variables that aren't the number of, aren't counting things, but are still discrete. They're not 100% of the time counted. That's just kind of an intuitive way to think about it. Well, let's talk about continuous variables. The length of your foot. Okay, your foot, we can measure it with a measuring tape. Okay, but when you go to a store, when they say, what size are you? You don't tell them that your foot is 8.75 inches long, right? What are they asking you when you say, what size are you? Are there an infinite number of options? I have weird feet. I'm 8.5 sometimes fit me, but 9 is too big. I'm 8 3/4, but no shoe, there's no shoe that's 8 3/4 inches long. I either have to choose 8.5 or 9. So shoe size is actually a discrete variable, because there isn't anything in between. It's your 8.5 or your 9. So shoe size is one of the few ones that I could think of that wasn't a counting of something. It's a hard one because counting is what we're doing most often, because your options are only 7, 7.5, 8, 8.5, 9, etc.
But if we were doing like the width of a foot, then that would be continuous, because
Yes.
we're taking into account everything in between, whereas discrete, it's just the concrete shoe size.
Correct.
Okay, awesome.
But since you talk about width, but you can also choose width in your shoes. But again, there's only like 4 options. There's narrow,
Well, like it
wide,
doesn't account for all the
wide.
in between.
Right, exactly. That's also discrete. There's only 4 options of widths of shoes you can pick. But if you're measuring the width of your foot, then these are all with the measuring tape.
How about like men's size in pants? Because for men, it's like the width of, like it goes like in centimeters or in inches, I think. But for women, it's totally different. They just have like 2, 4, 6.
Yeah, that's a good thinking. Except men and women, we both have the same issue in our pants that we have with shoes. there's only a static number. You're either a 32 or a 33. One might be too small and one might be too big. So you've got to choose, right? So in any time you're talking about a size of purchasing something to put on your body, that is actually going to be discrete because they all have that same thing that's happening with the shoe size. But if we're measuring our actual girth, that's continuous, but any sizes that you're talking about are going to be discrete. So let's go to example 1. Example 1 is a little bit of a confusing thing I want to make sure you're all clear about because we're doing different kinds of probability. In lessons 10 and 11, we were doing probability using two-way tables and Venn diagrams. And now we're back to frequency tables and relative frequency. When we're talking about discrete variables, the relative frequency is the probability distribution. Okay, and the reason why we can say that is because it's discrete. We either have 33 students in the class, or we have 34, or we have 35, or 36, or 37. These are discrete, right? And they're mutually exclusive. And that's what allows the frequency, the relative frequency, to be the probability. When we go to continuous variables, this is not going to be the case. Okay, because when you have continuous variables, we could have an infinite number of values between 33 and 34. And I realized that, by the way, on my solutions key, this was incorrect. This number was wrong here. We did a survey of all the statistics sections offered at DVC. We have 30 sections, and we recorded how many students were enrolled in each class. So there were 4 classes that had 33 students, 5 classes with 34 students, etc. Okay, so the relative frequency, remember, is the number that fits that category divided by the total. And we're told up here that there's 30 sections. So we know if we add up this frequency, that's going to equal 30. So the relative frequency of all these 30, 4 of them had 33. So what proportion of classes had 33 students enrolled? This is 4 of the 30 total classes here. So it's 4 out of 30 have 33 students. 5 out of the 30 have 34 students. 9 out of the 30 have 35. 8 out of the 30 have 36, and 4 out of the 30 have 37. That's a fraction, but when we're talking about probability, remember, we really want it as a decimal. In statistics, the answer is always a decimal, but we think in terms of percentages. But in order to get the decimal, we need the fraction. Okay, so this is 0.133, 0.167, 0.3, 0.267, and 0.133. Remember, your default is always going to be 3 decimal places, right? And it's 3 decimal places because then when we turn it into a percentage, we can get a little more detail than just 13%. We can say 13.3%. Okay, and what are these all going to add up to? Well, they should always add up to a roughly 100%, okay, or thereabouts. Now, this one happens to equal 100%, or if you're doing the decimals, it should be 1. When you're doing these relative frequencies, just note it's not always going to add up to exactly 1 and 100% because we've rounded all of these numbers. And when you're rounding, sometimes you'll get maybe 101% or maybe 97 or 98%. Okay, but you should get something very close to 100%. It's not always going to be exactly 100% because of all this rounding we're doing. So what's the probability that a randomly chosen class has an enrollment of 36? So we're finding the probability of 36 students in a class. And so I'm going to go up here. We're looking at this row here, and that probability is 0.267.
I have a quick question for number
Yes.
8. For number 8, I don't know if there was a mistake on the solutions because it said
Could
the
be.
answer was 0.167, but I thought it was 0.3 instead.
Oh, good catch. Thank you. You're absolutely correct. Thank you for pointing that out. On the solutions, we're asked to find the probability of a class having 35 students in it, and so that should be 0.3. I suspect I was looking at the one above it when I did that probability. You're absolutely correct. So that's a second typo I need to fix. Because we have this probability distribution, the frequency table rather, is the probability distribution. When we make this histogram, what's nice is we make the histogram using the n values. We make the histogram using the n values with the class size down here at the bottom. and how many satisfy in that class here. Because this is also the probability table, we can just look at these and saying this is probability of getting 33. A class of 33 is 0.133. So this frequency table now becomes a twofer. It's a frequency distribution, but it's also a relative frequency distribution. Okay, so we can look at it in terms of raw numbers, but we can also look at it in terms of proportions and probabilities. So we can just add these here, and then we can come look at this. So if we want to find the probability that a class has an enrollment of 35, here's 35. And here's my probability. Here's the probability that I get equals to 35. Now I want to find the probability that in a class has enrollment of 35 or fewer. Okay, so 35 or fewer, I can write this way. And just to remind you, these inequalities are going to be coming up a lot now. And remember that the alligator eats the bigger number. Do you remember that from your algebra class, to be able to tell which way the inequality goes? C is smaller, so this says 35 and smaller because the alligator is eating the 35. That means we're looking backwards, because we could also write this as that as well. Okay, so I want to make sure that you keep in mind that the alligator is facing the bigger one. So if the variable's on the other side, that means you're going below that 35. Okay, so we're looking at 35 or fewer. That means we're looking at these here, 35 or 34 or 33. Okay, remember, because they're mutually exclusive, this cannot be all three simultaneously. That's why it's an or. 33 or 34 or 35. So hopefully you notice and remember from lessons 10 and 11 that that's when we're adding the probabilities. Okay, so what's the probability of a class size of 35? That's 0.3, 0.167, 0.133. So the probability of getting a class size with 35 or fewer is 0.6. So in number 10, what's the probability has an enrollment of 36 or more? So 36 or more, again, this means either we're looking at 36 or 37. Okay, so this is the probability of a 36 or probability of getting 37. So that is 0.267 plus 0.133, which is 0.4. Notice what happened here. In the first one, 35 or fewer was here, and then the second question is 36 or more. Between those two, don't we have everything represented there? So with these discrete probabilities, that means what we have here is they are complements. And if you notice, that complementariness is also noted here because these add to 100 or to 1, right? 60 cents, that's 0.6. 1 minus 0.6 is 0.4. So we could also do it this way, because they're complements. Going to number 12 then, if we're looking at the probability of 35 or fewer students, 34 or fewer, and then more than 34 students, we're essentially doing the same thing we just did above with a slightly different order. Our options are 33, 34, 35, 36, or 37. 34 or fewer is these, 34 or 33. But more than 34 is 35, 36, or 37. That's kind of something unique with discrete probability. Expected value is the way we find averages with discrete variables. So that is to say, we expect the average class to have a certain number of students. You may have heard the average household in the U.S. has 2.3 children. How can you have 0.3 children? Well, that came from an expected value. They polled all the families using a census and figured out how many children were in the house, and they did this expected value. Okay, and we're going to do that same thing, except we're doing it with class size. We know what proportion each of these class sizes are, and we're going to figure out class size times the probability for each of these. So what was the probability of getting that 33 classes? Probability of 33 is 0.133. So we're doing 0.133 times 33. 0.167 times 34, 0.3 probability of getting 35, 0.267 probability of getting 36, and 0.133 probability of getting 37. And then we're going to add all of these up. What's nice is In my solutions, I calculated each of these values individually just so you could see what I'm getting. But with your graphing calculator, you can put all of this in all at the same time. 0.133 times 33 plus 0.167 times 34, and just put that in as one huge string, and you'll get 35.1. That means average statistics class at DVC has 35.1 students in it. Expected value is a weird thing, but just remember it really is just a way to find out on average how many kids are there in a household, how many students are in a class. Going forward to page 4, binomial probabilities are those that only have 2 outcomes. So a yes or no, right or wrong, left, right, Democrat, Republican, religious or not, pet owners or not. Discrete probability distribution would be, what kind of pet do you have? Cat, dog, lizard. And you remember I asked you that question on the first day of class. We could change that into a binomial probability distribution by just saying, do you have a pet? Yes or no. Okay, so again, we can look at the same variable 2 different ways. In these binomial probability distributions, the probability is also the distribution, but here's the difference. In this example we did just above, in this example, we had this table. We had all these different classes. We had a frequency. We could figure out the probability. The difference is we don't want to have to go through all this just to find the probability that a class has 35 students. We don't want to have to do this every single time. So what we're going to start doing, starting today, is we're going to use our graphing calculators to figure out probabilities. And that's what we're doing with binomial distributions and continuous probability distributions. The calculator doesn't have a mechanism for that beginning stuff we did, only for the binomials. So we're going to start using binomial distributions for our calculators, in our calculators. Okay, so I have this, in this example here, you were asked about random flights, whether or not a flight was on time. Okay, so we're looking at, is your flight on time, yes or no? Distribution of 10 flights. The probability of an on-time flight is 0.83. And you can actually look up on-time flights. Usually when you're booking your flight, we want to find the probability of getting 5 of those flights being on time. So of our 10 flights, what's the probability that 5 of them are on time? And you'll see, this is my simulation I did of 1,000 times. This, you see that probability you expect to be very small. We're going to use our calculator to figure it out. So we're using this thing called Binom PDF. Those of you with older calculators, it might be 0. We need to know how many trials there are, what the probability of success is, and how many successes we're interested in. Okay, so in this case here, we have 10 trials. The probability of success is 0.83, and we want to know the probability of 5 of those being on time. So of these 10 flights, what's the probability of getting 5 on time? Pretty much for the rest of the semester. You see here above the variables, the bars button, it says DISTR, D-I-S-T-R, that stands for distributions. So we're doing second vars to get to this distributions, and we're going to scroll up to binom, and binom stands for binomial, and you want the binom PDF. And like I said, it's either an A or a 0, and then press enter. Okay, and this is what you should get on your screen. All right, so the number of trials, actually, let me back up. You might not get this on your screen. Those of you with older calculators like mine, what you're going to get is just this. Okay, so you're going to put the same numbers in that I'm going to put in. It goes in the same order as what you see on your paper there. Number of trials, comma, and you've got to press the comma button, and that's the button right above the 7. We have 10 trials, probability of success 0.83, and X value is how many successes we're interested in. So for us, that's a 5, and then arrow down and press enter for paste. Those of us with older calculators, we have to input this part manually. So you'll put a 10, comma, 0.83, comma, 5, close parentheses, and press enter. The probability of having half our flights on time is 0.014. That's about 1%. And if you look at our simulation, that looks about right, doesn't it? Very small percentage. In number 29, we're asked to find all the probabilities for all those flights. So that's what we're going to do next. And I will absolutely, oh, I'm sorry, no, number 25, I meant. Number 25, we're asked to find the probabilities of 0 through 10 flights. So let me show you how to bring it back, because in each of these instances, the 10 is going to stay the same because we have 10 trials. The 0.83 is going to stay the same because all of these still have 83% probability of being on time. The only thing that's changing is the number of flights we want to know if we're on time, the X value. So just that last number is changing. So being able to bring back those previous ones are going to save you a ton of time. And let me show you how to do that. By the way, and if you haven't done this already, I would highly suggest you take one dedicated piece of paper that has just the calculator functions on it. Starting this lesson, and in every next lesson, we're going to be learning new functions to be using. So you really will save a lot of time if you can just go to your cheat sheet for what function to use for what type of activity, for what lesson. And also little hints to yourself for how to remember which is which. Like this one, we're doing binomial distribution, which is why our function is binom for binomial. Okay, so having those little hints will also help make your life a little easier. And this next thing I'm going to show you will work for all of our calculators. You see above the enter button, you see what it says? In blue or whatever color, it says entry. So if I press second enter, it brings back the last thing you put in there. And you can keep pressing second enter and we'll bring back the last 10 things you entered into the calculator. Okay, so I can just press that and then arrow backwards and change that 5 to a 0. And then just press enter and there's your probability of getting no flights on time, given 10 trials with an 83% success rate. Now, two things I want to point out. First of all, this is a 2 point something, which means if I take this as a decimal, this would be over 200%. Anytime the number before the decimal is anything other than 0, you need to go, whoa, wait a minute, hold up, something's happening here. And here you see I have a 2, keep reading, and here's this E. What this E stands for is scientific notation. If you remember that, this means times 10 to the negative 8, which means this number is actually a 0.000000, there we go, 2015939. That's what that number really means. That is ridiculously small. What we do is we call this just effectively 0. If you were taking chemistry or biology, you can use numbers that fine of a detailed value. Here in statistics, we don't have that ability. We cannot get that close to a number. We can only do 3 decimal places. Beyond that, we don't have the power in our numbers to give that detail. We take this E in statistics and we translate it to mean effectively 0. And that's how you can remember the E. It just means effectively 0. On your sheet then, we'll just write a 0 or effectively 0. So we can do the same thing and keep going with the 1. 1 is effectively 0 as well. Anytime there's a number other than 0, keep reading and look for that E. If you don't see that E, you've done something wrong up here, more than likely. So keep going. Number 2, we can do 2 successes, effectively 0. 3 successes, effectively 0. Okay, this is getting boring. Let's do 9 successes. Now we have an actual number.
I just had a quick question on how you got 0.83.
Because I told you, because we're looking at this one flight between Oakland and LA, and that flight is only on time 83% of the time. And the 10 is, if I'm looking at 10 flights that I just took in the last year, 83% of the time those flights are on time. What is the probability that only one of those 10 flights will be on time, or 2 of them will be on time? That's what the X value is representing. Okay, so what I would like you to do then is practice using this binomial PDF, and the P means we're just doing one number at a time. In the next lesson, we're going to be looking at a range of numbers like we did at the beginning of class. The probability of less than 3 flights, more than 3 flights. That's a different function. Right now, we're just doing exactly 3 flights. Okay, so I'd like you to finish those probabilities in 25, and then also example 5 using the binom PDF. And before I start doing the statistics, one thing I do first is I just straight up clear my screen, because here's what happens to me every once in a while. I'll press a random button and then I'll go to this distribution with Binom PDF. Okay, and then we'll do this. I'll press enter. You see, it gives me that different number. Sometimes I'll get an error as well, depending on the function that I'm using. But you see that my value changed because it's taking this as a multiplication. So always start out with a cleared screen. So now if I could press second enter, it's going to bring that one back. But if I don't touch anything else and just press second enter a second time or a third time, now I'm back to the regular one without the number in the front of it. Okay, so welcome back. I just want to point out just a couple things. Number 29, finding the expected value. I did all these intermediate calculations. This is the number of on-time flights times the probability. So in each of these cases, basically, we're taking these two numbers and multiplying them together, and I put them, that product, down here. Okay, so I'm taking 1 times 0, that's 0. Right, that's the number here. So essentially, we're just taking each of these numbers and multiplying them together. I did the intermediate calculations just so you could see what it looks like. The great thing about having these graphing calculators is you can actually put this product all in your calculator as one long string. Now these first four, we know all of those are going to add up to 0 because 0 times any number is always 0. But you could do 4 times 0.02 plus 5 times 0.014 plus 6 times 0.057 plus 7 times what, plus this, plus that, and press enter, and what you'll get out is 8.3. And now you know if you make one little mistake, you can bring it back using second enter and fix your little mistake by just typing over it or inserting a number. Out of our 10 flights, we expect an average of 8.3 flights to be on time, and that makes sense because 83% of our flights are going to be on time, and if we have 10 of them, 83% of 10 is 8.3. So when we have a binomial distribution, it's going to turn out that we don't have to do all these steps anymore. Turns out with a binomial distribution, we just take the probability times however many there are, and that's going to be our expected value. So it's not a coincidence that we got 8.3. That's something that we're going to touch on in more detail in lesson 13. Lesson 13 is a continuation of these binomials. In this lesson, we were figuring out the probability of just one of these happening. But in the next lesson, we're going to be figuring out what's called cumulative probabilities. 8 or more flights are on time, or less than 6 flights are on time. So instead of just finding one, we're going to do more than one. If you look at your calculator, we were using Binom PDF. Below that is Binom CDF, and that C stands for cumulative. And cumulative means an inequality, a range of values. And we're going to start doing the cumulative probability with binomials, but in lesson 14, we're going to stick with that cumulative probability, but for continuous variables. So that's your preview of what's happening for the next lesson. Basically, from here on out, the calculator is going to be doing all the work for us. All right, that's the end of class, everybody. Don't forget, I'll be around for the next 20 minutes if you have questions or need any help. And I'm always here before class, too, if you have questions or need help. And have a great weekend and have fun with your project.